we're going to do today is nothing new when we combine transformations, but we're bringing all of it in at the same time. So we're going to be looking at graphs that have been transformed through translations, reflections, and or stretches. Okay? So in general, y equals f of x could be transformed to y equals a times f of b times x minus h, lots of brackets in there, plus k. Okay. A. What does that tell us about? Yes, so A is the absolute value of A, rather, is the vertical stretch factor. If A is negative, there's also a vertical translation. Okay, so this is the vertical stretch factor is going to equal the absolute value of A. And if A is less than 0, there's also a reflection. Okay? What about B? So B is going to affect horizontal reflections and stretches. So let's first talk about the horizontal stretch factor. What would the horizontal stretch factor be? Yeah, it's the reciprocal of B, and we typically talk about stretch factors as being positive values. So I'm going to put absolute value symbols around there to make sure that it's positive. And then also, if B is less than 0, you'd also have a reflection. Okay? H. What's H? Yep. Horizontal translation. I'm running out of space, so I'm just going to abbreviate. If H is positive, then what would happen? Okay, so I'm not talking about this sign. I want to know if the actual H value is positive. It's going to go right? Because the negative sign is built in. So if H is greater than 0, it's going to go right. If H is less than 0, it's going to go left, right? And if H is less than, let's say H is -5, this would be x minus -5, right? So yeah, the sign inside the bracket sort of doesn't correlate to the direction that it moves, but that's because in the format of the equation, the negative sign is already in there. Okay? And then finally, K is the vertical translation. And if K is positive, it's going to go up. And if K is negative, it's going to go down by K units. Okay, so here's a question. Do you think that we can sort of start anywhere and do the reflections and translations and stretches and all of those different transformations in any order? Probably not, because otherwise I wouldn't have asked the question, right? Okay, so what would your gut instinct be? What do you think you'd have to do? Yeah?
I'd probably translate it first, just because that's what we learned first.
Okay, translate first, because that's what we learned first. Anyone else? Yeah, well, although this one says translated 3 units to the left, then reflected in the y-axis, right? So if you're given a description that has order, you have to follow that order. But if you're just given this equation, then there is an order that must be followed, and it actually has to do with order of operations, BEDMAS, right? So stretches and reflections involve a multiplication. Translations means you're moving it left or right, so you're adding so many units to the x value and so many units to the y value, so those get done second. Okay. Now, if you're graphing these things, we kind of say do stretches first and then do reflections, but the reality is you could do them both at the same time. And particularly if you're using mapping notation to take certain points and map them somewhere else, you certainly would do those two things at the same time. But, you know, I would encourage you, if you're kind of doing these things methodically, one thing at a time, to not do too many steps at once. Okay? So just to show that this would, you know, that these would not be the same, we're going to take the same function. First, we're going to reflect it in the y-axis, and then translate it 3 units left. Okay, so this point is going to go here. This point is going to go here. This point's going to go here. I'm just flipping over. Okay, and then I have to take that whole thing and move every single point 3 units left. So 1, 2, 3. 1, 2, 3. And maybe I'll make these a little bigger. 1, 2, 3. This one I already moved. Where am I? Here, let's do this one. 1, 2, 3. 1, 2, 3. Okay. Now, if we translate it left first and then reflect it, we're going to get something that looks different. So actually, I'm going to do these in different colors because otherwise I'm going to lose track of what's what. So 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. And then I'm going to switch colors and maybe do this in green, the reflection. So this point will move here. This point is on the axis, so it's going to stay as an invariant point. This point will go here. This point will go, it's 4 away from the axis, so it's got to be 4 away from the axis on the other side. This one is 5 away, so it'll go there. And I think that's it. Okay, but these are not in the same spot, right? In fact, the difference in the translation from one to the other is 6 units, because you've kind of gone 3 in the wrong direction, right? So yes, the order that you perform these translations and reflections and stretches in does make a difference. And when you're given something in this form, the general rule of thumb is to do stretches first, then reflections, then translations. But in reality, these could be done in either order or at the same time. Okay. Now, using mapping notation, if you have y equals f of x, and that is transformed to y equals a f of b times x minus h plus k. this point will map to. Now let's just think horizontally first. The two parameters that will affect the graph horizontally are B and H. We have to deal with B first. So if we just think about there being either a horizontal stretch or a reflection horizontally, what will X map to? If we're just thinking about the B part, what would we have to multiply X by? The reciprocal, yeah, 1 over B. Okay, and then we're moving H units left to right. Sorry, plus H. Because again, if H is positive, you move to the right, but the negative sign's already built in. Okay? Y, if we have either a vertical stretch and or vertical reflection, Y will map, if we do that part first, to AY. And then we're moving up or down by K units, so plus a K. And if K is negative, we'll move down, and this will turn into a negative value. Okay? Now, I know this looks a little bit confusing because, for example, if you look at the horizontal piece, it doesn't really follow the same pattern as the vertical because we multiply X by the reciprocal of B, and then we add H, but there's a negative sign here, right? And then for Y, we just multiply by A and add K, right? And again, that all has to do with the fact that the transformations that are applied horizontally are attached to the X variable on that side of the equation, whereas the transformations for vertically have been moved to the other side of the equation for Y. If we were to rewrite this, then the same sort of rules would apply, where you'd multiply by the reciprocal of whatever was attached to the Y, and you'd subtract K or whatever, right? So it's really, that's the only reason why that's happening, and you just kind of have to know that, right? This would be something that is worth remembering because a lot of problems can be solved using mapping notation, right? If you are ever in a bind and you don't know what a function is going to look like when you graph a transformation and you can do mapping notation, you can just pick a few points and map one to the other and literally plug in the original X value into this, plug the original Y value into this. Okay, and there are quite a few problems that I even solve using mapping notation. Okay, now I kind of don't know if I want to go on this side note, but I think someone mentioned we do translations first and then the stretches. So when we were looking at graphing quadratics in 20-1, then we sort of got away with that by moving the vertex to the new spot and then doing the stretches. However, we assume when it's in that new spot that that's like the new origin. And so the stretches that are applied would be applied from the graph from the origin. Okay, so it is a way of doing it as well, in particular if you have a function that you're familiar with the basic function. So I'm just going to give you an example because I feel like I'm talking about it and people are like, what? If you have y equals x squared, okay, there's basically 5 points that you want to remember. And of course, you could do more. But as long as you can remember these 5 points, -2, 4, -1, oh, I didn't do that. Why did that happen? There we go. Okay. You can graph the basic function. Okay. So if you had something like this, okay, this is written in vertex form. And if you think about all of the different parameters that we've spoken about, essentially what's happening, h is -3, we're moving 3 units left, 1 unit down, and then there's a vertical stretch factor of 2 as well. Okay, so there's 2 ways of doing this. You could, and in 20-1, what we kind of, the way I've always done it is move, find your new vertex, and here's -1. There's your new vertex. If you now assume that this is the new origin and start counting your points from here, then you can kind of stretch these points, right? So if there's a vertical stretch of 2, -1, 1 is going to move to -1, 2, because the y values are going to be doubled. However, if we start here, this is our origin, we can do it that way. 1 left, 2 up. Okay? If we do the point -2, 4, from here we're counting left 2. This is like our new starting point. Left 2, and then we would have to double the 4 up to make it 8 up. But we're not going 8 up from 0, we're going 8 up from -1. So like 1, 2, 3, 4, 5, 6, 7, 8. It's going to be off the page. Okay, and then similarly, 1 right, 2 up, 2 right, 8 up. Okay, so you can do it that way, but you have to kind of really know your stuff and make sure that you understand that if you do the translation first, this is now your new starting point, right? So you're not stretching -3, -1 and doubling that and making -3, -2, for example. You're not stretching from this point. This is your new 0, 0. Okay? Alternatively, though, if you kind of follow the guidelines that I spoke about, you can just stretch this guy, right? And this is now 2, 8. So you stretch first. And then you take the whole thing and shift it 3 units left and 1 down, right? And then you're going to end up in the same spot. It's just going to go like that. Okay? So for certain functions, if you really understand the basic function, personally, I find it easier to sort of translate to my new starting point first, but then I'm stretching from that point as if that point is the origin. Okay? The reason why I mention this is that if you keep going in math from here, right, if you continue to take further math courses, you don't get like a graphing calculator anymore, right? You really have to have an understanding of the basic functions like y equals x, y equals x squared, y equals the square root of x, y equals absolute value of x. When we start building in other types of functions, there will be other basic functions as well. And then if you understand those basic functions and what they look like graphically and you can picture them, and you understand transformations, you can transform whatever you want. The same rules always apply. Okay? But if this is kind of really confusing, or if you kind of thought, wait, with quadratics, we did it differently, where we found our new starting point first and then we stretched, this is why, right? It's not quite as black and white as we sometimes make it out to seem, and there's more than one way of doing a certain problem. Okay? For now, though, I'm going to stick to this. Okay. So the first thing I want to do is just look at a function. We don't know what the function is, and be able to describe the transformations. And then also, well, I don't actually say here to do a mapping notation, but I think I'd like to do that as well. Okay? So we have y plus 5 equals 4 times f of -x. Where would you start here? Yeah. subtract 5. Make sure y is isolated. And actually, there's one more point that I really didn't emphasize, but I want to do it now. This b value has to be factored out. Okay, so when we look at a horizontal translation, it only applies when the coefficient of x is 1. So if there's any number in front, we've got to factor that out. And we'll see that in a moment. But for now, we're just going to isolate y. So we'll subtract 5 from both sides, and we will get y equals 4 f of negative x minus 5. Okay? So if you can remember stretches, reflections, translations, right? This is sort of the order that we want to describe these transformations in. Okay? So are there any stretches that we need to talk about? Yep. What has been stretched? Vertical stretch factor of 4. Okay? Okay. Is that it for stretches? Yep. Any reflections? Yes, there's a reflection horizontally in the y-axis, right? And if you kind of like, I messed up the point 9, 1 to be 1, 9, so I do that kind of thing too. Just draw an axis and then flip your hand over it and see what you're flipping over. Yeah?
I always just write x values or reflections of the y-axis. Is that, like, do we, like, for this test, would you want us to say horizontal reflection?
No.
Okay.
And in fact, you could just say I'm reflecting over the y-axis and that covers your bases, right? Now to just say a horizontal reflection doesn't actually cover your bases because there are situations where you don't actually reflect horizontally over the x-axis. You could reflect over a different line like x equals 2, right? If I reflect over x equals 2, this would move over there. So this piece is important, okay? If you don't include the word horizontal, there's only really one way to reflect over the y-axis, and that's horizontally, okay? All right, and then what about translations? 5 down. Yep. And the word down implies that we're going vertically, right? So you could put in that word as well, vertically translated 5 down, but it's not necessary. Okay? Okay, so mapping notation. The point x, y. So think about x first. We have a horizontal, x will be horizontal reflection. So what's going to happen to the x value? Negative x, yeah. Is there any horizontal translation? No, so that's it. And then in terms of y, first we stretch by a factor of 4, so y is going to become 4y, and then we move 5 down, minus 5. Okay. Let's look at B. So do you think there's any sort of work to be done first before we start to write these things out for B? Yeah.
Are we supposed to factor,
Yeah.
just divide by 2, so it's an x plus 7, and then x plus 7?
Yeah, so we don't divide by 2, but we factor it out. Because if we left it in as 14, we might mistake the translation for being 14 left, when in fact that's not the case, right? So make sure that this is factored. Okay, so I'm going to rewrite this as y equals negative f of 2 times x plus 7. And this was just me. There we go. Let's take that out. Okay. So let's start with stretches. So you're looking at your A and your B value. And for stretches, we really just look at the magnitude, right? The numerical, the absolute value, rather than whether there's a positive or a negative. Okay? So are there any stretches here? Yes? Horizontal stretch by a factor of 1/2. Good. Okay. Any reflections? Any reflections? Yep. X-axis, right? Because A is -1. Okay. And then any translations? 7 left, yes. Okay, so the point xy, okay, so we have to think horizontally first. So there's a stretch factor of 1/2, and it's moving 7 left. We got to take the original x value, multiply it by 1/2, and then move it left, -7. Okay. Vertically, the only thing that's happening is the reflection in the x-axis. There's no vertical stretch, there's no vertical translation, so y will move to -y. Okay. So I want to look at C and just sort of start it together, and then I'm going to get you guys to finish it. Because we have these decimal values for A and B. And personally, I find it easiest to write these in fraction form if I can. You don't have to, I suppose, but you know, for example, if you're describing the horizontal stretch factor, you don't want to say it's 1/0.25. It's kind of like bad math grammar, right? You want to say it's 4. So what I would do is convert these into fractions. So 1.75 is like 1 3/4 or 7/4. You don't have to. And then 0.25, that's 1/4. And the other thing is, if you like find this really hard, you can always use the fraction button on your calculator. And do you guys know how to do that? Yes? Anyone not know? Oh, I still have to get my Castio subscription. Shoot, I forgot to do that yesterday. So I'll have to, I can show you though. So if you put in 1.75 and then use the math button and hit number 1, it'll convert that into a reduced fraction. Okay? So like, don't spend too much time worrying over this. If you have to spend a lot of time converting a decimal to a fraction, use this or just leave it in decimal form. Okay? All right, so I am going to let you guys finish these last two. So let's start it with this. Determine the equation for each transformed function. And I know some of you guys got started on this yesterday. That's totally fine. But I do want to go over this one and particularly the ones on the next page. So the y equals f of x is stretched horizontally by a factor of 6, reflected in the x-axis, and translated 7 units down. Okay, so let's pick these apart one by one and try and figure out, based on the description of the transformation, what the parameters a, b, c, or a, b, h, and k would be. Okay, so stretched horizontally by a factor of 6. What does that tell us about? Which parameter tells us about a horizontal stretch? Yep, B, right? If it's stretched horizontally by a factor of 6, uh-oh. Okay, I guess I have to switch to the pen. Then what's the value of B? 1/6. Okay? Reflected in the x-axis, so like this. A is going to be negative, right? So what I kind of like to do actually is when I'm writing out my values of A, B, and C, and D, I scan the stretches and the reflections first, because then I know whether or not the A or B value is negative, right? So I'm not, if you read the whole thing first, we're not told about a vertical stretch. So we know that the magnitude of A is 1, but because it's reflected in the x-axis, it's -1. Okay? And then it's translated 7 units down. What does that tell us? Yeah, K is -7. Okay? Now, if there's no, for example, in this case, horizontal translation, you're not going to be said, there's no horizontal translation here, right? You just have to assume that if in the description there's nothing said about a horizontal translation, that there isn't one. Okay? So if we wanted to write this in the form y equals a f of b times x minus h plus k, it's really just a matter of filling in the values for a, b, h, and k. Okay, so this is going to be y equals, you could write -1 f of x or just negative f of x. B is 1/6. Okay, now h is 0, so you could just write x. And then plus -7 is -7. Okay, so far so good? All right. So now what we want to do is a little more than just writing the equation out in terms of f of x. We're given an actual function, which is y equals the absolute value of x, and we want to write the new equation out if these transformations are applied to it. Okay? So this can be a little tricky to do, but a good starting place is to start in the same way as we did in the previous example, where you write it out in terms of f of x first, and then you can put all of those values into the actual equation. Okay? So here we can see this function is reflected in the y-axis, stretched vertically by a factor of 1/2, and translated 3 units to the right. Okay? So there's one reflection, one stretch, and a translation. Okay, so if it's reflected in the y-axis, what type of a reflection is that? It's horizontal, yeah. So that's going to affect the B value, right? Now, I didn't see anything in here about a horizontal stretch. So what I can tell from this is that B is -1. Or, I mean, actually, technically it's 1/-1. But 1/-1 is -1. Okay? Stretched vertically by a factor of 1/2. What does that tell us? Yeah. Yep. So it's kind of being like compressed a little bit. It's going to be shorter, right? What parameter does that tell us about? A, right? And the value of A is 1/2, right? Okay, translated 3 units to the right. Yep. K equals 3. H, yeah. Okay, so now what we're looking at is we have an original function y equals f of x, which in this case is the absolute value of x. And we're transforming that into y equals a 1/2 f of b, which is -1, times, now this part's important, x minus h, so x minus 3. Really important that that piece is in brackets because the translation applies when the coefficient of x is 1. And so if x is being multiplied by any value, that has to be factored out. Yeah?
Would it be positive 3 since you have to?
Okay, good question. So if you expanded it out, yes. If you remove the brackets, it would be -1 plus 3. Okay? But to see what the transformation is, that value has to be factored out anyway. Okay? And then there's no vertical translation, so that's it. Okay? Now if we wanted to write this out in terms of this function, the format is going to sort of be a function plus k. Now, there's a little caveat to this because whatever you put in the function, you have to replace the x, every x that you see, with whatever is inside the brackets. Okay, so if I'm starting to write this out in terms of the absolute value of x, it's a, which is 1/2. Then the function absolute value of x, we don't have to worry about k here because k is 0, but I'm replacing x, because f of x is absolute value of x, f of this, the inside part, gets substituted for wherever you see an x in the equation. Okay, so I'm going to put a big absolute value sign, set that up for myself first, and then I'm going to take this piece, plunk it in there. -1 times x minus 3. Okay, and yeah, at this stage, if you wanted to distribute the -1 in and make it a 1/2 absolute value of -x plus 3, you can absolutely do that. Okay, but this is always a good starting place. Start with the general function notation, then apply it to the actual equation that you're given. Yes?
So do we expand it or no?
I'm not going to ask you to expand here, right? Because I just asked for an equation. If I just ask for an equation, yeah, and to be honest, if you're going to end up doing anything with this equation, it's better for this -1 to be factored out anyway. Because let's say we wanted to graph this by hand, right? We need to know that this is a transformation of the absolute value of x. We want to very clearly see, okay, that's a reflection, but the translation is going right? Sometimes if you distribute in and this ends up being a +3, you may mix that up and think that it's going to go left.
Don't do it then.
So if you did it, it wouldn't be wrong, right? If I asked you for an equation and you expanded, it's not going to be wrong. I'm not going to mark that wrong because it's equivalent to what we see here, right? It's a question, though, of what are you going to do with this, right? Are we going to try and graph a transformation of the original? Because if we're going to try and graph a transformation of the original, personally, if I were to do that, I would want it on this form, in this form so I can very clearly see both the magnitude and the direction that the horizontal translation, what's happening with that, right? And if this was any other number other than 1, if you expanded, you might mistake the number over here to be the horizontal translation, when in fact the horizontal translation is when it's in factored form. Okay, so I know that that's not a black and white answer, but if I ask you for an equation and you give me an equation that is correct, that's fine, right? Would you want to expand all the time? Kind of depends on what you want to do with it. I would argue that most of the time, the answer would be no, right? And particularly, I'm just thinking ahead a little bit into if you continue doing math, don't have the use of a graphing calculator, then you want to really clearly be able to see the exact transformations that are taking place. Okay. All good questions though. All right, so next, y equals x squared is reflected in the x-axis, stretched horizontally by a factor of 3, and translated so that the vertex is at 10, negative 4. Okay, so let's first work out our parameters. So if you reflect in the x-axis, what type of a, sorry, down. What type of a reflection is that?
Negative
Yeah, vertical, right? So A is going to be negative, and I don't see a vertical stretch, so I know here A is negative 1. Okay, now it's stretched horizontally by a factor of 3. So what does that tell me? Yep.
it's 1 over 3.
B is 1 over 3. Yeah. And translated so that the vertex is at 10, negative 4. So ordinarily, if you were looking at y equals x squared, where would the vertex be? 0, 0. So 0 has 0, 0, that vertex has moved to 10, negative 4. And by the way, the point 0, 0 is going to stay 0, 0 after reflections and stretches are applied, right? Because if you're at the point 0, 0, you multiply that by, I don't know, 1/3 or negative 1, you're still at 0, 0. Okay, so that's a really good point to keep in mind when you are thinking about where's the translation happening. Okay, so what does this tell us about the translation? Where's this thing moving to?
Right down.
Yeah, 10 right, 4 down. Okay, so this means h is 10 and k is negative 4. Okay, so I'm going to just start to set this up with my original function, and then I'm going to transform it into y equals a f of b times x minus h plus k. So I'll put in all my values. Instead of negative 1 here, I'm just going to put negative because that's usually the way that you'll see it. F of b 1/3 times x minus h, x minus 10, plus negative 4. It's just going to be minus 4. But if you write plus negative 4, that's good. Okay, and now we actually have to write the equation for this thing. Okay, so this is not, it's a bit tricky, right? It's not as easy as it may seem, but this is always the a value. This part's the function, and then plus k. Now a caveat is that within the function, you have to replace all of the x values with that, right? So the way that I like to set this up, the a and the k are the easy part. Oh, I meant to do a space here, sorry. Right? This is just a negative value or negative 1. This is minus 4, right? So if you want, you just make this minus 4, that's fine. What I do with the function is I rewrite the function as exactly as I see it, but I replace all the x's with a set of brackets. So the function is x squared. I'm going to put in here brackets squared. And then inside the brackets, I'm going to put whatever I see here. 1/3 times x minus 10. Okay? So all together, I mean, you wouldn't normally put these fill in the blanks in there, but this is going to be negative 1/3 times x minus 10 squared minus 4. Okay, now I'm going to leave it like that for now. If you actually saw this function written out, you may see, for example, that the 1/3 has been squared. This might be distributed, right? And that might become 1/9. Okay, now written that way, that now becomes the a value. So this transformation, this stretch of horizontal stretch by a factor of 3, you can either see it as a horizontal stretch or a vertical compression, right? If you think of a parabola and you stretch it out this way, it's the same as compressing it this way. So this is one of those other functions where you can see the stretch going both ways. Okay, but written with a horizontal stretch, this is what it would look like. Okay? All right, questions so far? Okay, so the key point, 110, is on the graph of y equals f of x. Determine the coordinates of its image point under each transformation. Okay, so what we want to do here is we want to know, where does the point 110 move to after these transformations have been applied? Okay, so let's think in terms of mapping notation, right? Now, before I do that, though, I'm going to make sure of two things. Number one, I want y to be isolated. So I'm going to have to subtract 4 here. And then the second thing that you need to look for is to make sure that the b value has been factored out. Okay? So I am just going to rewrite this as y equals f of x minus 5 minus 4. Okay? So what's happening to the x values? These are all translations. Yeah, it's moving right. So the original x value is going to become x plus 5, and then the y value is going down, y minus 4. Okay? So the point 110 is going to move to, now with this one you probably don't need to do this, but when you get all the transformations happening at one time, you may literally want to put 1 in there, 1 plus 5, and then 10 minus 4. With this one, you could probably do it in your head. Okay? So that's the point 6, 6. Okay? So far, so good? Okay, so in B, y is isolated. If I look at the coefficient of x inside, that's a 1, so that's good. Okay? So what's happening here? Yeah, there's a vertical reflection. So that's going to affect the y values, right? There's no stretch. There's no vertical translation. So you could even just put negative y in there if you know that that's true, right? And then in terms of the x values, x minus 12. Right? So 110 is going to move to 1 minus 12, negative 10. So that's the point negative 11, negative 10. Okay? All right, what about this next one? Yeah, we have to make sure that this is factored out so that when I'm looking to the horizontal translation, the coefficient within the bracket is 1. Okay, so y equals 3, f of, you could write this as 0.5 or 1/2, whatever you want. Okay, now think about this. Half times what is 10? 20. Okay, so let's try and figure out horizontally what's happening first. Are there any horizontal stretches or reflections? Yep. Because this is 0.5, right? So how much is it? Now it's not negative, so there's no reflection. What is it being stretched by? 2. Yeah. So this, the stretch is 1 over the absolute value of b, right? So if b is 0.5, 1 over 0.5 is 2. So this is going to become 2x. And then is that it for x, or is there anything else happening? 20 left. So minus 20. And then what about y? Times 3. Yeah. Okay. So this point is going to move to 2 times 1 minus 20, 3 times 10. And that's 2 minus 20 is negative 18, 30. Okay, so for a multiple choice question, you could be asked, you know, in this type of equation compared to f of x, where would the point 110 go to? Right? That's, you know, or if both values are positive, like the 6, 6, could be a numerical response too. All right. So let's try another one. The following transformations are performed on the graph y equals f of x to obtain the graph y equals g of x. Okay, so here's what's happening. There is a vertical stretch by a factor of 6 about the y-axis, reflection in the x-axis, vertical translation 5 down, horizontal translation 3 left. Okay, so vertical stretch about the y-axis, stretched vertically. What does that tell us? The a value. Yeah, so right now, we should also look to the reflections. The reflection is happening in the x-axis. So it's a vertical, yeah, right? It's a vertical reflection. Okay, so both of these tell us that the a value is negative 6. Okay, vertical translation 5 down. What does that tell us? What parameter? Yep. And then horizontal 3 left. H is negative 3. Okay, so first step is to write g of x in terms of f of x. So we are going to basically fill in our parameters. G of x equals a, which is negative 6, f of bx. So we don't have a b value in here, so the b value is 1. And then x minus negative 3, and then plus k, plus negative 5, right? Now, usually we simplify the signs so that you don't have 2 signs, you only have 1. But again, this is just a reinforcement as to why the h value, why this sign looks positive even though it moves left. Yeah?
If you say g of x in terms of fx, do you do negative 6g or is it negative 6f?
So it's negative 6f because the transformations are being applied to f of x. So we're saying how is f of x changing to create this new function g of x? Okay? All right, if the point C, 4, 2 is on the graph of f of x, using mapping notation, find the coordinates of the point G. So let's start with the point, or the coordinates on g of x, I should say. Let's start with mapping notation. And you guys, one thing you can remember, like this is also worthwhile remembering, this is going to move to 1 over b plus h and ay plus k. Oh, sorry, 1 over bx. I missed the x, that's important. Okay, so if you can also remember that, that would be something worth like writing down at the top of your page, as well as the general format of the function with all of the parameters. you know, f of a times f of b times x minus h plus k. Okay? So the point xy on the original is going to move, okay, 1 over b. b is 1, so we don't need to worry about that. X plus h was negative 3. So x plus negative 3 is x minus 3. A is negative 6, negative 6y, and then k is negative 5, so minus 5. Okay? And then when you want to know where the point 4, 2 is going to move to, you can use these expressions and fill in x equals 4 and y equals 2. Right? So this is going to become 4 minus 3, because it's x minus 3, comma, negative 6 times y, negative 6 times 2, minus 5. I'm running out of room. Okay, and then simplify that. So that's the point 1. Negative 12 minus 5 is negative 17. Okay, and then finally, we are going to, if we're given the defined function f of x equals the square root of x, how would we write out the equation for g of x? So I want to kind of have this up there at the same time. Okay, so g of x is negative 6 times the function. So I'm going to put a big negative 6 on the outside. And then I have to multiply it by the function. The function is the square, y equals the square root of x. So I'm going to put a big square root symbol, but remember to replace all of your x's with brackets. And then after that, we subtract 5. Yep.
Is the bracket thing, like, do you have to have that? Or?
You don't have to. Right? And with this one, it's pretty simple. Where the brackets sometimes come in handy is, like, let's say your function was x squared minus 5x plus 7. And you have to replace all of the x's with another function or another expression. Right? It's not required, but yeah.
Where'd the 12 come from?
Oh, shoot. Where did I get the 12 from? Is there a 12 somewhere on here? I don't know how my brain works. Plus 3. There we go. Okay. Now this happens to be a radical function. We're going to have a whole unit on radical functions. I think it's our 3rd unit. So we're going to learn more about this kind of thing then. So just like foreshadowing, what would happen to the domain and range? How would that change? That kind of thing. Minimum and maximum values. Endpoints. Okay. So far, so good? All right. So let's look now what happens graphically. Okay? So when you're thinking graphically, you may be asked to do 2 things. Number 1, you may be given 2 functions, graphs of 2 functions, and have to determine what are the transformations that have taken place, and maybe can I write an equation for the transformed graph in terms of the original. So you have to be able to look at a graph and figure out the translations that have taken place, or not translations plus all the other ones, transformations that have taken place. Okay? And then you also have to be able to take a function, be told about a bunch of transformations, and then graph the transformed graph. Okay? So we're going to start with, what if we want to write an equation and compare 2 graphs and write an equation for one in terms of the other? Okay? Now, this can be it can be a little tricky sometimes depending on the function. But what I would encourage you to do is find key points on the original and look at where they've moved to. Okay? So, whoops. This is really bad grammar. Compare where they've moved to. I think I added in a preposition. Is that what it's called? Anyway, whatever. Hopefully you guys know what I mean. Now, some hints for good points to look at. Okay? Vertices, vertexes. Look for the vertex. Endpoints, right? If you think about y equals the square root of x, that goes like that. There's an endpoint right here. Where's the new endpoint? Another point that comes in handy is the point 0, 0. Because if you can see, if 0, 0 is on the original function, and then that point moves somewhere else, remember that stretches and reflections do not affect the point 0, 0. And so that actually can tell you about your translations. So look at the origin. That's a really good one. Okay. The other thing that can really help is to, and this doesn't apply for all functions, but if you have a function that's in a limited domain or range, look at the height and the width of the original compared to the transformed. Okay. So this is one thing you can do. You can also compare heights and or widths. Okay? All right. So let's look at an example. Okay, so we're looking at the blue graph y equals f of x is the original, and g of x is the transformed graph. And we know that because we're asked to write, or here we're told g of x is a transformation of f of x. So f of x was the original, now we are transforming it. Okay, so firstly, have there been any reflections? No, there's no reflections here. It's in the same orientation. I mean, technically, I suppose there could be a horizontal horizontal reflection because this is symmetrical about the y-axis, but we're not going to make our life complicated. Let's not worry about that. We won't put in extra information if we don't have to. So let's start. Maybe there have been some stretches. This thing looks like it's taller and more narrow than the original. So I'm going to compare the heights and the widths first. Okay, so if I look at the original y equals f of x, the height is 3. And here, it is. Oh, I can't count. Thank you for correcting me, because sometimes classes just let me go on and on and on and on, and everybody knows that something is obviously wrong. So anyway, okay. What about g of x? What's the height? 8. Yeah. And I'm just thinking, actually, h is probably a bad letter to use because you might confuse that with the horizontal translation. I'll use a capital H maybe to differentiate. Okay. What about the width? This width is 8. And this one is 2. Okay, so we've ruled out reflections. There has been a vertical stretch factor, though. What is the vertical stretch factor here? Yeah. And that is our A value. Okay. Horizontally, what's the stretch factor? 1/4. It's a quarter the width of the original. So horizontal stretch factor is 1/4. So what's the B value? 4. Okay, now Translation. Translations. What point would you look to figure out the translations? The origin, yeah, this happens to also be the vertex, so we can clearly see where the vertex has moved to. And it looks like it has gone 7 left and up 2. Okay, so 7 left, up 2. So this means that left, that's h. H is -7. This is k. K is 2. Okay, so I would never go just from looking at the graph directly into here, right? You want to lay out a few things first. So do a brief note about all of the transformations you see, right? Then maybe talk about, oh, well, if the vertical stretch factor is 2, A is going to be 2, and so on and so forth for each parameter. Then you can fill it into g of x equals a times f of b times x minus h plus k, right? So g of x is going to be a is 2, f of b is 4, times x minus h. In this case, this is going to become x plus 7, because we're subtracting -7. Okay, and then plus 2. Okay, and I mean, I used square brackets there because I just looked at the format and I was like, oh yeah, that's a good idea. But you don't have to. You can use curved brackets if you want. It's kind of nice though. It makes it visually, you can see it a little bit more clearly. Okay? All right. So the graph y equals k of x represents a transformation of f of x equals x squared. Okay, so we can see this is a quadratic function, and f of x is y equals x squared. That's the original. That's not given to us. So you guys kind of are expected to know what that looks like, what the key points would be. Okay, and that basic quadratic function comes up all the time. So you're going to see it over and over and over again. And so where I would start is, well, where would you start? Yeah, so before I do, I want to know what y equals x squared looks like, right? I'm going to sketch that. Sketch. Okay, let's see if my colors work today. Oh, yes. Okay, something happened when I turn it off and on again and again. So my key points are 0, 0, -1, 1. -1 squared is 1. 1, 1. 2, 4. That's probably good enough. Okay, and we have a couple of key points on this other function as well. Okay, so firstly, are there any reflections that have happened? Yes. What type of reflection? Vertical. So A is going to be negative. Okay, so we know that. We want to keep that in mind. Okay. What about stretches? Relative to the vertex, if I were to flip this around, are these points in the same position as these ones? No. So you may even want to see for the stretch, like what if I flipped this around? If you reflect it, you have these points, right? So when you're trying to figure out the stretch for something like this that's continuous, where you can't really compare heights, for example, or widths, because the height of both of these is infinite and the width of both of these is also infinite, then I would compare these key points. So here's the origin. How does this point compare to this one? in terms of the displacement from the origin. This one is 1 left, 1 down. This point is 1 left, 2 down, right? And this one is 1 right, 2 down. Okay? The next one is 2 left, 4 down. What about this guy? Relative to my new vertex. It's 2 left and 8 down. Right? So this is 2, this is 8. This is 1, this is 4. Okay? So what type of stretch is happening? It's vertical. Yeah. It's being stretched vertically. The x values don't change, but the length of the y values, the distance, is double. Okay? So we know that there's a vertical stretch factor of 2 because those vertical distances have doubled from where they were to the origin, or I suppose in this case like the x-axis, that axis that the vertex lies on. And also there's a vertical stretch. Sorry, reflection. Okay, so both of these together, what parameter can we figure out based on that information? Yeah.
A is -2.
Yeah. Okay. Now, the translations. What are the translations? Uh-oh. Oh, I gotta pause. Why did I stop the recording? Oh, did I stop it and start it? All right, so we were talking about translation. So which point would you look at to figure out translations? Yeah, vertex, right? So it looks like it's gone left 5. I'm in green. And then up 7. Okay, so that means that h is -5 and k is, -5. And k is 7. Okay, so writing k of x in terms of f of x. So this is that format that we keep using over and over. This one over here, we're writing in terms of, in function notation. And we just have to plunk in all our parameters. K of x equals a, -2, times f of b. B is just 1 in this case. X minus h, x minus -5 is x plus 5. And then plus 7. Okay, so good question. Would you square the brackets? In this notation, no. Because all you're doing in this notation essentially is saying, what do I multiply the original function by? What do I replace the original x's with? And then what do I add at the end? Okay? When we write this in terms of x, yes, we're going to square it. Yeah, okay? So k of x in terms of x is the a value, -2 times the function. The function is x squared. So this is going to be something squared plus 7. And that something is x plus 5. Okay? All right, now, if 525 lies on f of x, which it does, 5 squared is 25, find the corresponding point on k of x. Occasionally you see people like trying to actually work it out graphically. That's going to be like, it's going to go off the page. Okay, so use some mapping notation here, right? So xy moves to 1 over bx plus h, ay plus k. Right? And if you write that out as well as just a guide or a format for you to follow, you don't have to, you know, start from scratch every time, remembering where does each parameter go. If the b value is 2, the horizontal stretch factor is half. It's just in there for you. Okay? So xy, horizontally, there was no stretch or reflection. So this is just going to be x, but then we're moving 5 left. And then a is 2y plus 7. Okay, so this point, 525, will become 5 minus 5. Oh, whoops. -2 times 25 plus 7. You guys all okay over there? Yeah? Okay. So that's 5 minus 5 is 0. This is -50 plus 7 is -43. Okay? All right. So I think, let me just see. Yeah, we're almost done. Okay, so the other thing that you might have to do with graphs is have an original function, be given transformations, either a description of them or the notation with a, b, h, and k, and then draw the new function. Okay? Now, when you're sketching transformations, I highly, highly, highly recommend using mapping notation. Okay? And then just map one point to another point, one point to another point. If it's a with something like this, it's pretty easy because we're just going to be looking at 4 points, mapping them to 4 other points, connecting the dots. If it's something continuous, you can pick a couple of key points on the original function and then map them somewhere else, and you should be able to see the shape of the graph. Okay? So the graph of the function y equals f of x is given. Sketch the graph of y minus 1 equals f of -2x plus 6. Okay. So mapping notation, xy is going to move to 1 over b x plus h, ay plus k. Okay? Are we ready to do that yet? No, there's some work that needs to be done, right? Because we need, number one, y to be isolated, and we want the b value to be factored out if it's not. So I'm going to add 1 to both sides. Okay, and then here, I want to factor out -2 from -2x plus 6. What would go in here? X minus 3, yeah. Because -2 times -3 is positive 6. Okay? So the point xy is going to move to, more specifically, 1 over b, 1 over -2x, and then h is 3 plus 3. And then ay, so a is just 1 in this case, so just y plus k plus 1. Okay? Now, what I'm going to do is make a list of points on the original. I like almost setting it up like a table of values, but it's really this point's mapping to this point. So let's see, the first point is -2, 4, 6, 3. And you don't have to necessarily do them in order as long as they're all down there. The next one, -2, -4, -3. Okay, the third one is 0, 0. That's nice. And then finally, 2, 4, negative 4. Okay, did I make any mistakes? Oh, shoot. What did I do? 6? Oh, it's negative 6. Thank you. Yeah. Okay, so now I'm just going to plunk this in x and y value into here, right? So this point will map to 1 over negative 2 times negative 6 plus 3, comma, 3 plus 1. Okay, and then I would like rewrite it out so you actually know where it goes, right? So let's see, negative a half times negative 6 is 3, plus 3 is 6, and then this one's pretty easy. 3 plus 1 is 4. Okay, next, negative 4, negative 3. So this will map to 1 over negative 2 times negative 4 plus 3, comma, negative 3 plus 1. Which is, let's see, that's 2 plus 3 is 5. And then negative 3 plus 1 is negative 2. Okay, 0, 0, that's nice because we don't have to worry about the stretch or reflections. So this one's actually just going to go to 3, 1, right? Can you guys all see that? That's okay? All right, this one's going to go to 3, 1. And then finally, 2, negative 4 is going to move to negative a half times 2 plus 3, comma, negative 4 plus 1, which is, okay, so that's negative 1 plus 3 is 2, and then negative 3. Okay, so I am going to now sketch all these, or plot all these points, I suppose, and then connect them. So the first one is 6, 4. 2, 4, 6, 2, 4. Okay. The next one is 5, negative 2. 2, 4, 5, negative 2. 3, 1. 3, 1. And then 2, negative 3. Okay, and then there we go. Okay. Yes.
Is that value the last blue one, like the last value? Is it 4 and negative 4? That's 2 and negative 4.
Oh, shoot. Yeah. I asked you guys if I made mistakes, and you just said the 1. This point is 4, negative 4. Oh, okay, that's okay. Easy to fix. Okay, negative a half times 4 plus 3. So that's okay. Negative 2 plus 3 is 1. So that's going to be 1, negative 3. 1, negative 3. That's okay. Now the other thing that you may want to think about, just to check this out, is if you look at the notation over here, you should at the very least be able to recognize, okay, there's going to be a horizontal stretch of a half, so this thing's going to become narrower, and the orientation will also reflect, right? And that is, in fact, true. This thing is more narrow, and it's kind of flipped around in terms of the orientation. Okay, kind of looks like the Harry Potter scar. All right. last question. Okay, so firstly, I don't know what happened here, but this should be absolute value of x. And there you go. Sometimes when you copy and paste from Word, from one version of Word to another, things move around. Okay, so now we are given a description of the function f of x equals absolute value of x. And then we need to determine an equation. Okay, so let's just read this through. The graph of the function f of x equals absolute value of x is stretched horizontally by a factor of a half about the y-axis, reflected about the y-axis, then translated 6 units to the left and 3 units down to form the transformed function g of x. Determine the simplified equation of g of x in the form y equals a times the absolute value of x minus h plus k. Okay, so again, going straight from the description right into the equation is not an easy thing to do, and you guys can already see, like, I'm not stellar at not making mistakes. So I would make sure that you pick apart every bit of the description and then say how that's going to affect the parameter. Okay, so the graph of the function f of x is stretched horizontally by a factor of 1/2. Okay, horizontal stretch factor is 1/2. Okay, about the y-axis, reflected about the y-axis. What type of a reflection is that? Horizontal. Oh, what? Horizontal reflection. Okay, so based on these two transformations, what can we conclude? So this tells us about our b value. B is for sure negative. It's -2, right? Because the b value is the reciprocal of the stretch, and the stretch is the reciprocal of the b value. So b equals -2. Okay. What else? Yes. H is -6. Yeah, translated 6 units to the left, 3 units down. So 3 left. Six down. Okay.
So it's 6 left.
Oh, seriously. I have a reading problem. 6 left, 3 down. Okay, -6, -3. Whew. Okay, so let's start with g of x equals a f of b times x minus h plus k. Let's start with that and fill in all of our a's, b's, h's, and k's. Okay, so g of x is going to equal a, there's no a value, so that's just 1, absolute value of -2 times x minus 3 plus 6 plus k. No, plus 3. So I just realized, actually, I swear I'm not doing this on purpose. I'm thinking ahead. That's my problem. I got to be in the moment. Okay, so I realized that I actually just went from this format right to here, right? Without going in between. Do you want to, should I slow that down a little bit? Okay, let's slow that down. So, okay, this is a good thing to do. Let's start from scratch. There we go. Okay. A is 1. You could put a 1 there if you want. You don't have to. F of B, -2 times x plus 6 minus 3. Okay. You guys ready? Shh. Okay, so here we go. We now need to write this in terms of x because we're asked for this format. Okay, so g of x is going to equal 1 times, this is where the function goes, minus 3. Shh. Now the absolute value, the function is absolute value of x. So I'm going to put some nice big absolute value symbols and a set of brackets. And inside those brackets, I'm going to put this. Okay. Is that the format that we're asked for? No, it's not. Okay, so let's just think about this. If you consider y equals absolute value of x, okay, so what we talked about in terms of, let's not worry about the translation right now. Let's just worry about the stretch and the reflection. So what we figured out is that there's a horizontal stretch factor of 1/2. Shh, guys, I know that a lot of you guys are talking about this, but it's really distracting for me when there's so many side conversations going on. Okay, so if we take this base function, what we figured out was there is a horizontal stretch factor of 1/2. Okay, so if we take all of these points, vertically they're not going to move, but horizontally they become half of what they were. Okay, same thing here. Okay, now, is there another way to see that transformation? It's being stretched horizontally like this. Is there another way of, yeah, we could also stretch it vertically. Vertically, these values are doubling. So for this particular function, this horizontal stretch factor of 1/2 is the same as a vertical stretch factor of 2. Okay, now there's also the reflection piece. What happens when you take the absolute value of x and reflect it in the y-axis? If I take something like this and reflect it there, what am I going to see? Same thing. Sorry, I meant to say y-axis, right? It's getting reflected in the y-axis. Yeah, you're going to see exactly the same thing. Okay? And that is because there is symmetry to this function. And it happens to be symmetrical about the y-axis. Okay? So, in fact, the reflection in the y-axis doesn't make a difference at all. Okay? So we can actually take this, and I'll just rewrite this nicely without all the extra stuff, absolute value of negative 2 times x plus 6 minus 3. And bring that negative 2 out and make it positive. Okay, now if you think about it this way as well, another way to think about this is if you think about absolute value of a product, because this is a product. It's negative 2 times x plus 6. Is it true that you can do this? Is that true? It is, yeah. So think about it this way. Let's suppose A and B are both positive, like the absolute value of 2 times 3. That's still 2 times 3 is 6, right? If one of them, if they're both negative, then the answer is positive. This is still going to be like negative 2 becomes 2 times negative 3 becomes 6. Or sorry, becomes 3. 2 times 3 is 6, right? If one of them is positive, one of them is negative, let's say this is negative 2 and 3, this would be the absolute value of negative 6, which is 6. This would be the absolute value of negative 2, which is 2, times the absolute value of 3, which is 3. That's 6, okay? So we are allowed to do this. If we're taking the absolute value of a product, we can break that up into the product of multiple absolute values. It works, okay? Going back to here, what you may sort of think about in between, or another way of thinking about this, if you don't want to think about it in terms of, okay, this horizontal stretch is the same as this vertical stretch, you can also take this and say this is equal to the absolute value of negative 2 times the absolute value of x plus 6 minus 3. Because if I take the absolute value of two things multiplied together, I can break that into two absolute values and multiply those together. And that is 2 absolute value of x plus 6 minus 3. So why did we do that? That's a good question. Why did we do that? Because part of the understanding around transformations is you have to be able to understand that there are multiple ways to be able to see a transformed function, right? Sometimes that's not true. Sometimes there's only one way of seeing it. And usually that's for something like this, where it's a piecewise function, right? So it was this guy here. We could clearly see that there's a height change and a width change, right? But the reality is that most of the time, we don't see these types of functions. We see continuous functions. Or, I mean, this is continuous, but it's over a restricted domain, okay? We don't, more often than not, we see functions with a domain that's not restricted. And so when that happens, and when there is symmetry to the graph, there are usually multiple ways of interpreting a transformation. And so one of the skills that you guys have to be able to do is to be able to communicate what those multiple ways are. Okay? Now, if this was like a multiple choice question, you could certainly graph this on your graphing calculator, right? Because we figured it out in terms of a horizontal reflection and stretch, because that's the description that was given. And then one of the answers would be this. So you could graph all the answers as well and see which two graphs overlap, right? So remember, if it's a multiple choice question, the answer is somewhere on the page. And you can often use technology to match up question to answer. Okay? All right, so I am going to stop there.